Imagine peering far beyond the known edges of our solar system, past Neptune, past Pluto, into a realm so remote, so cold, and so mysterious that it's been compared to a cosmic twilight zone. Now imagine we've just thrown open a new door into that darkness, discovering an object so distant and so strange that it could upend everything astronomers thought they knew about the outer reaches of our cosmic neighborhood. What if, right now, everything we thought we understood about our solar system's frontier was suddenly in question? In May 2025, the International Astronomical Union made an announcement that sent shockwaves through the astronomical community. A new world, a trans-Neptunian object dubbed 2017 OF201, had been spotted on the far fringes of the Sun's influence. At an estimated 700 kilometers in diameter, it rivals some of our best-known dwarf planets. But what truly makes it remarkable is its orbit, a staggering 25,000 years for a single trip around the Sun, with its most distant point stretching 1,600 times farther out than Earth's own orbit. For perspective, if Earth's path was a small circle, 2017 OF201 traces a ring so vast it defies comprehension. Most of its lifetime, it's simply invisible, so far away that we'd never know it existed. And yet, right now, we're among the lucky generations alive to catch it near its closest point to us. But this cosmic discovery is about more than just a new point on the map. It calls into question some of our most cherished astronomical theories, most notably the tantalizing idea that there's a hidden, massive planet, Planet 9, lurking beyond Pluto, shepherding distant objects into mysterious patterns. Suddenly, with one icy world, the story of our solar system's outer frontier is being rewritten. And behind the scenes, the tools that enabled this detection weren't billion-dollar missions, but data anyone on Earth could access. So, how did we find 2017 OF201? Why does it shake the foundations of planetary science? And what does it teach us about the hidden depths of our own backyard in space? Stay with us as we uncover the global race to map the unknown, the technological leaps driving new discoveries, and the economic and philosophical stakes of understanding our furthest horizons. To understand why this new object matters so much, we need to rewind almost 2 centuries, to a strange period when the boundaries of the solar system seemed both tantalizingly close and hopelessly out of reach. The story starts with the search for so-called Planet X, a hunt that, for generations, lived somewhere between science and obsession. Back in the 19th century, astronomers noticed oddities in the orbits of Uranus and Neptune. These anomalies suggested the gravitational tug of an unknown, hidden world. The race was on. Visionaries like Percival Lowell built massive observatories, chasing shadows and whispers of a planet that lurked beyond our reach. In 1930, Clyde Tombaugh finally discovered Pluto at Lowell's observatory. There was jubilation. Finally, the solar system's edge had been found, or so they thought. But Pluto, as it turned out, was too small and light to explain the orbital quirks of Uranus and Neptune. The hunt for Planet X simmered on, taking on new shapes as science advanced. For decades, textbooks printed maps that ended at Pluto, picturing a cold, simple frontier. But lurking just beyond, a far more crowded and dynamic region was waiting to be discovered. The real revolution began in 1992 when astronomers Dave Jewett and Jane Liu detected Albion, the first in a swarm of icy bodies orbiting beyond Neptune. Suddenly, the Kuiper belt came into focus, a vast, toroidal halo of small worlds, remnants from the solar system's earliest days. Its true extent? Up to 55 times farther from the Sun than Earth. Scores, then hundreds, then thousands of trans-Neptunian objects, TNOs, have since been catalogued, each adding a pixel to the blurry edge of our planetary portrait. Quoting David Jewett of UCLA, the trans-Neptunian region has proven to be a valuable probe to test models of the formation and evolution of the solar system. The Kuiper belt wasn't just a planetary graveyard, it was a living archive of our system's childhood. But 2 discoveries forced astronomers to rethink everything. First, the detection of Eris in 2005, a TNO even larger than Pluto, sparked a fierce debate over what really constitutes a planet. The resulting reclassification thrilled some, frustrated others, and put Pluto in the middle of a lively global argument. But more importantly, it revealed the dazzling diversity and complexity of the solar system's outskirts. These are not just frozen leftovers. They're laboratories where cosmic chemistry and ancient history unfold in slow motion. Over time, as telescopes grew more powerful, it became clear that this region was home to several distinct populations. Some of these objects remained locked in resonance with Neptune, their orbits sculpted by the gas giant's gravitational dance. Others followed wild, eccentric paths, scattered by planetary migrations billions of years ago, or perhaps nudged by the gravity of stars passing near our sun. One puzzle, above all, has teased and tormented astronomers for the last decade: the apparent clustering of extreme trans-Neptunian objects, or ETNOs. These ETNOs, with orbits stretching hundreds or even thousands of astronomical units away, seem to group towards certain sky directions, as if shepherded by an invisible architect. This tantalizing pattern led two astronomers, Mike Brown and Konstantin Batygin at Caltech, to hypothesize the existence of Planet 9, a Neptune-sized world, lurking unseen, responsible for aligning these outer orbits. Mike Brown, famous for his role in Pluto's demotion, once told reporters, "The real answer here is to not get too hung up on definitions. We all understand the intent of the hydrostatic equilibrium point, and the intent is clearly to include Mercury and the Moon." The Planet 9 hypothesis electrified the astronomical community and the public alike. Citizen scientists, engineers, and researchers joined the hunt, combing vast datasets and operating robotic telescopes in the hope of spotting this elusive world. The internet buzzed with wild theories. Was there a true ninth planet, the remnant of the sun's lost twin, or even the fossil of a failed star? Yet, as more TNOs were discovered, doubts began to surface. Some objects defied the predicted patterns. The orbital complexity of the Kuiper belt, the influence of Neptune, and the randomizing effects of billions of years posed major challenges. And then, in 2025, the discovery of 2017 OF201 landed like a meteorite in the middle of this debate. So, what exactly did astronomers find? 2017. OF201 is not just another icy rock. Its orbit is mind-boggling. At its closest, it sweeps just beyond Pluto, 44.5 times farther than Earth from the Sun. Similar radiation, similar region. But at its farthest, it drifts a monstrous 1,600 times that distance, far into the cosmic dark, where the Sun is just another star in the sky. Sihao Cheng, the Discovery Team leader, put it like this: 2017 OF201 spends only 1% of its orbital time close enough to us to be detectable. The presence of this single object suggests that there could be another 100 or so other objects with similar orbit and size. They are just too far away to be detectable now. Let that sink in. If there's one, there could be hundreds. Each could be vast, some large enough to qualify as full-on dwarf planets. And yet, in all of human history, we've only glimpsed this one because of a lucky intersection, a cosmic game of hide-and-seek. Here's the twist. The very pattern of 2017 OF201's orbit doesn't match the prediction that led to the Planet 9 theory. Instead of aligning with other ETNOs, it's an outlier, a rebel in the crowd. Jiaxuan Li of Princeton University explains, many extreme TNOs have orbits that appear to cluster in specific orientations, but 2017 OF201 deviates from this, challenging the Planet 9 hypothesis. It's a cosmic prankster, defying the neat models that scientists hoped would lead to a simple answer. This throws a wrench in the works. If more objects like 2017 OF201 are out there, are models of the solar system's outer edge, the very ones that have guided billions of dollars in research and mission planning, may need to be rewritten from scratch. Are we looking for the wrong thing, or is Planet 9 simply hiding somewhere even further out? Perhaps the most exciting lesson isn't about objects or orbits, but about how we discover them. Remarkably, 2017 OF201 was not found with the latest ultra-powerful space telescopes. Instead, it was uncovered by searching through archival data, existing images taken by the Blanco and CFHT telescopes, available to anyone with enough skill to run the algorithms. Jiaxuan Li notes, all the data we use to identify and characterize this object are archival data that are available to anyone, not only professional astronomers. This means that groundbreaking discoveries aren't limited to those with access to the world's largest telescopes. This democratization of discovery is both exhilarating and humbling. It means the next big breakthrough could come as easily from an ambitious undergraduate or a passionate amateur as from the world's top research labs. The race to understand our solar system is no longer limited by physical access or budgets. It's about creativity, computational skill, and the power of open knowledge. But with each new find comes new questions, and the conflicts cut deep. For every astronomer delighted by the mystery, there are those frustrated by the complexity. If 2017 OF201's orbit is an outlier, are the patterns suggesting Planet 9 merely a statistical fluke? Or does the very existence of such orbits hint at forces even stranger, passing stars, rogue planets, long-lost companions of the Sun? And what about the practical side? The stakes aren't just academic. Billions of dollars are at play in funding telescope time, building new observatories, and proposing space missions. The Vera C. Rubin Observatory, for example, is about to come online, promising to flood the world with even more outer solar system data. Would confirming or refuting Planet 9's existence change the course of these investments? Could the next big discovery, the one that truly rewrites our textbooks, be hiding in the very data we already have, just waiting for a clever algorithm or a determined outsider to find it? This is the crossroads where science and opportunity meet. We're standing on the edge of a cosmic ocean, maps in hand, with the faint outlines of new continents shimmering on the horizon. The discovery of 2017 OF201 is both a milestone and a mystery, a signal that our solar system is even wilder and richer than we ever imagined. So now, we're left with a tantalizing cliffhanger. As astronomers prepare for the next wave of discoveries, will new trans-Neptunian worlds confirm the existence of a hidden giant planet, or force us to abandon the hunt for Planet 9 altogether? Or even wilder, will we uncover clues to forces and events that have shaped our system since the dawn of time? The next chapter in this cosmic detective story is about to begin. But what happens next? Now that the discovery of 2017 OF201 has not only upended the neat narrative about Planet 9, but also suggested a lurking population of similar objects, the race is on, not just to find the next one, but to rewrite our cosmic maps from the outer edge inwards. The astronomical community is buzzing. If one object like 2017 OF201, spending merely a sliver of its 25,000-year journey close enough to be seen, has been spotted in archival data, then it's statistically likely there are hundreds more out there, silent, frozen witnesses to our solar system's birth and evolution. Hao Cheng's words echo in every research hall. The presence of this single object suggests that there could be another 100 or so other objects with similar orbit and size. The implication is dizzying. For every strange world we glimpse, many more could be passing through the cosmic wilderness, just beneath our detection thresholds. Here's the twist. 2017 OF201 doesn't just add a new member to the solar system's roster. It threatens to scatter the pieces of the puzzle we thought we were assembling. The highly elongated, tilted, and unconventional orbit doesn't fit the patterns that led astronomers toward the Planet 9 theory. Instead, it's as though nature has scribbled over the careful orbital clustering we'd use to draw a line towards an unseen super-Earth far beyond Neptune. If more such outliers emerge, the statistical basis for Planet 9 begins to vanish. Jiaxuan Li, its co-discoverer, doesn't mince words. Many extreme TNOs have orbits that appear to cluster in specific orientations, but 2017 OF201 deviates from this, challenging the Planet 9 hypothesis. It's as if the solar system is holding out on us, withholding the final answer until we've looked harder, deeper, and more creatively than ever before. So what are the possible futures? In one scenario, researchers trawl through petabytes of old and new data. The Vera C. Rubin Observatory comes online, scanning the southern sky every few nights. The James Webb Space Telescope, JWST, with its frigid optics and infrared gaze, peers even further out. Hundreds of new TNOs are logged. Perhaps, buried in the statistics, the elusive clustering re-emerges. Planet 9 gets a second wind, hiding just out of sight but shaping the orbits of these distant objects into a cosmic fingerprint only a true planet could leave. Alternatively, the flood of new discoveries cracks the theory wide open. Orbits that were supposed to align instead reveal chaos, not order. The hypothesis collapses, not because nature is wrong, but because our understanding was too limited, our sample size too small. In this world, the outer solar system is more anarchic and less orchestrated than we dared imagine, shaped by ancient gravitational billiards. A passing star a billion years ago, a wayward giant planet ejected early on, Neptune's slow migration sculpting the icy debris in unpredictable ways. It gets even more fascinating. Each new TNO isn't just a dot on a distant star chart. It's a laboratory frozen in the deep freeze of time. JWST's detection of methanol ice on other TNOs, for instance, hints at complex chemistry, organic molecules that might mirror the prehistory of worlds like ours. Arakoth, flown past by New Horizons, preserves primordial material, offering a window into the solar system's infancy. With every remote detection, astronomers are learning how little they know. As David Jewett, one of the field's pioneers, says, the trans-Neptunian region has proven to be a valuable probe to test models of the formation and evolution of the solar system. These objects are not just space rubble, they are archives, crystallized storytellers of cosmic history. But there are risks too. If the Planet 9 hypothesis falls, some decades' worth of work and expectation might have been chasing a mirage, forcing scientists to rethink not just where we look, but how we look. Models of planetary migration, the history of close stellar encounters, even the origins of the Oort cloud may need radical revision. Some skeptics have always warned, extraordinary claims require extraordinary evidence. For now, 2017 OF201 is a cosmic curveball. There are tantalizing opportunities, though. The key is unlocking more discoveries, fast. The computational tools used to spot 2017 OF201 in archival data are now accessible to anyone. Every new detection could shift the balance. It's a democratization of discovery. University teams, citizen astronomers, and high school students with the right code and curiosity can search for the solar system's next oddball. As Lee confirms, all the data we use to identify and characterize this object are archival data that are available to anyone, not only professional astronomers. This new age isn't just about telescopes. It's about algorithms, machine learning sifting through oceans of pixels, looking for the dim, moving signals that hint at distant worlds. It's about collaboration, open data, and dogged persistence. Imagine it. Somewhere, right now, a college student could be downloading sky survey images from the Blanco telescope, running code late into the night, and being the first human ever to glimpse a forgotten world. It could be you. So what does all this mean for the rest of us, those of us grounded on Earth, gazing up and wondering what lies beyond the edge? First, it's a lesson in humility. Even after centuries of charting the heavens, the most basic inventory of our own solar system is unfinished. We don't know how many planets, dwarfs, or planetesimals drift in the far shadows beyond Pluto. Nature is more mysterious and more surprising than we give it credit for. Second, this saga is a masterclass in the power of curiosity-driven science and the importance of looking again at what we already have. The discovery of 2017 OF201 didn't require a new billion-dollar instrument. It took rethinking existing data. It's proof that sometimes the greatest revolutions in knowledge come not from building something new, but from asking new questions of old material. Third, anyone can take part. The digital transformation of astronomy means that discoveries are increasingly open source. There's a growing movement of amateur scientists contributing real findings. The next 2017 OF201 might not be found by a Nobel laureate, but by someone in their garage with a fast computer and a faster mind. The universe is not owned. Discovery is truly everyone's game. And there's a practical lesson too. Uncertainty is not failure. When cherished models get disrupted, when evidence doesn't fit the theory, it's not a setback, but an opportunity. The greatest leaps in science come when we ask, what did we miss? For those interested in fields beyond astronomy, this story is a call to interrogate assumptions, to embrace anomalies, and to hunt for meaning in the data ignored by others. The outer solar system is a metaphor for all the unknowns in our lives, vast, unexplored, and brimming with surprises waiting just out of reach. As we close, let's answer the burning question. Will the next wave of discoveries vindicate the search for Planet 9 or force us to abandon it altogether? The truth is, nobody knows for sure. 2017 OF201 has put the odds even. Every new TNO uncovered could be a vote for or against the existence of a hidden planet. With so many possible orbits and histories, nature keeps her secret for now. But the chase is far from over. In the next decade, a flood of data from the Vera C. Rubin Observatory could double or triple the catalog of known trans-Neptunian objects. Each one will be scrutinized, their orbits mapped with increasing precision, their surfaces probed for ice, organics, and clues to formation. The pattern, if it's there, may reappear or vanish for good, or yarn. The secret that few talk about? Even if Planet 9 is never found, these distant objects are the real gold mine, fossils from the solar system's dawn, untouched by sunlight for eons. They offer a time capsule, a direct link to the earliest days of our planetary neighborhood, and perhaps to the chemistry that seeded life. So, whether the elusive Planet 9 is out there or not, The edge of our solar system has never been more exciting or more open for exploration. The story doesn't end, it just gets richer, with every pixel, every algorithm, every curious mind. Want to be part of this cosmic hunt? Check the open data platforms from observatories worldwide. Join the forums where amateur and professional astronomers swap leads. Try your hand at detecting movement in astronomical survey images. Even history-changing discoveries can start with a single click. And don't forget to subscribe for more deep dives into the solar system's biggest mysteries, as we chase the shadows at the edge of the sun's domain. If you liked this journey, hit like, share your theories in the comments, and tell us, what would you name the next lost world?